Okay, so we're moving on to another topic, which is graph coloring. So yeah, so first we're going to talk about vertex coloring, then we're going to talk about edge coloring. So today is going to be about coloring vertices of a graph. So proper coloring of a graph G is a function f from the vertices of G. So I'll just write to like the function maps the vertices of G to C, where C is a set of colors. So usually we'll just use like the numbers 1 up to something, but in principle you could call you could literally call the colors like red, blue, green, whatever. Doesn't really matter. So C is a set of colors. Such that f of u is not equal to f of v for all edges uv of the graph. Okay, we've kind of seen this already. We've talked about like the 3 coloring problem and stuff like that. So also it's useful to have a notion of a proper K coloring is a proper coloring where the number of colors is K. Okay, so then the kind of key parameter that we want to focus on in well, at least vertex coloring is the chromatic number. So, so the chromatic number of G is, so the notation is chi of G, and it's defined to be the minimum K such that G has a proper K coloring. Okay. How many of you are familiar with this, at least a little bit? Okay, so most people, I think. Okay, so I mean, the idea is, computing the chromatic number is an optimization problem, right? You have an input, which is a graph. You want to color it with the smallest number of colors you can, with this restriction that you're not allowed, like adjacent vertices are not allowed to get the same color, right? So as an example, we've talked a lot about bipartite graphs. Bipartite graph is the same thing as a graph with chromatic number at most 2, right? So G is bipartite if and only if the chromatic number of G is at most 2, right? I say at most 2 because it could be 1 if there are no edges at all, right? Yeah, if you think about it, if it's bipartite, you could color the first color class, or the first side of the bipartition with red and the other one with blue. All the edges go across. And then like vice versa, if it's chromatic number at most 2, take the red vertices, that's one side of the bipartition, the blue vertices are the other side. Okay. So yeah, the topic of graph coloring is like a really, really broad topic. There's so many different directions you could go in. We're going to focus mainly on things that are, I think, very kind of closely connected to the stuff we've been doing in this course. Like in particular, like computing the problem of, so this optimization problem of computing the chromatic number is NP hard. So like, generally speaking, I'm not going to be able to give you an algorithm for solving this, right? Because actually we've already, I think, talked about the fact that determining, so the three colorability problem, so determining whether the chromatic number is at most 3 is NP complete. Okay, and so if it's NP complete to determine whether the chromatic number is at most 3 or at least 4, like, or I guess I should say, if the decision problem for determining if the chromatic number is at most 3 is NP complete, then yeah, computing this number is going to be NP hard. Right. So, we're not going to be able to compute this, but we will be able to kind of understand it, maybe for like a restricted family of graphs. There are some kind of easy upper and, or let's say lower bounds that you could prove on the chromatic number. I'm not sure if I defined this before, but let's do it now anyway. So a clique in G is a set C of vertices of G such that UV is an edge for all pairs of vertices in C. Of course, well, I guess I want distinct vertices because, like, we're not having vertices adjacent to themselves. So, okay, so like a clique. So if I could have a sort of larger graph here. But like these 4 vertices would form a clique because, yeah, pairwise, they're all adjacent to each other, right? One kind of standard, maybe I should, so I should define the clique number. So omega of G is the maximum K such that G has a clique with K vertices. So this is called the clique number. Okay. So yeah, in this example, omega would be equal to 4 because this thing has a clique with 4 vertices and it doesn't have any bigger ones. Can anyone see a relationship between like the chromatic number and the clique number? Yeah. Yeah, exactly. So yeah, always the chromatic number is at least the clique number. So yeah, in case you didn't hear that, then yeah, it's because in a clique, every pair of vertices has to get a different color because they're all adjacent. So like, I guess by pigeonhole or something, you'd have to use at least omega of G colors just to color the clique. And so to color the whole graph, you need at least that many colors, right? So this is like one kind of, we can think of this like a trivial bound, trivial lower bound on the chromatic number. There's another kind of trivial lower bound which is worth knowing. So I think we defined this before, like alpha of G is the max K such that G has a stable set with K vertices. So like a stable set is an independent set, right? Okay. So now I want to get some kind of a relationship between the chromatic number and this. So this is like the stability number. But this relationship is also going to involve, like I want some kind of thing, some kind of inequality, a lower bound on this involving this and this. Can anyone see one? So I want to have chromatic number at least some kind of combination of these things. I'm not telling you what it is, but yeah. Yeah. Do you see why that might be the case, or? And none of them are bigger.
The max place is that like you have like a stable set on like those keywords, some sort of divided by the number of like.
Yeah, I think you've got the idea that.
It could be partitioned into pieces of size of alpha G that would have exactly.
Yeah.
And if any of those partitions have, or partitioned into stable sets, if any of those stable sets have size less than alpha G, it must be greater.
It'll be even better. Yeah, exactly. So just to kind of repeat that, like, I mean, what is a proper coloring? Like each color class, like if I look at the vertices of a color 1, the vertices of color 2, those are all independent or stable sets. And so yeah, by pigeonhole, like if I, how do I say this? So I'm partitioning the vertices into stable sets. Each stable set has at most this size, right? So the number of stable sets you're going to need by pigeonhole is at least like, since all of them have at most that size, it's n over the number of vertices over that, right? So like you said, this would only be equality if every stable set in your coloring is actually maximum size, right? Okay, so this is like another kind of trivial lower bound. Okay, and yeah, so the key kind of insight here is that proper coloring is a partition into stable sets. Those are the same thing, right? Okay. All right, so I want to now introduce something called perfect graphs. For that, I need one more definition. So for a set of vertices, the subgraph of G induced by S is the graph with vertex set S and edge set, well, it's all of the edges of the graph where the endpoints are in S. So it's the set of all UV in the edge set of G such that U and V are both in S. Okay, and the notation for this is G with square brackets S. Okay. right? So the idea is like I specify a set of vertices, and then I take those vertices, and I have to take all the edges inside, right? So if my S was like these three vertices, then, and this is the graph G, then G of S, or G, the subgraph of G induced by S would be like that. Right, so you're not allowed to like, you can just, you're just deleting some vertices of the graph and leaving S behind. You're not allowed to delete any edges inside of S. Okay. Okay, so now I'm going to define something called a perfect graph, which honestly, it might seem a little bit like an arbitrary definition, but it turns out that it's like kind of a magical class of graphs that kind of covers a lot of things that come up, we've already seen in this course, but also a lot of things that show up in different areas of discrete math. They can be kind of represented in terms of perfect graphs. So a graph G is perfect. So this is just a definition. If the chromatic number of the subgraph of G induced by S equals the clique number of the subgraph of G induced by S for all subsets S of the vertex set. Okay. A little bit of an abstract definition, but basically, if you remember this kind of trivial lower bound, right? What I'm saying is that, well, first of all, I want G to satisfy this trivial lower bound with equality. I want chromatic number to equal clique number, but I also want this to like also work for all the induced subgraphs of G. So if you like zoom in on a set of vertices, I want those vertices by themselves to satisfy this equals that. Like everywhere you look in the graph, chromatic number equals clique number. Okay. Here's like a very basic class of examples. Bipartite graphs. Because like any induced subgraph of a bipartite graph is still bipartite. And like the chromatic number is 2. The clique number, well, okay, unless, bipartite graphs are slightly annoying because if it has no edges, the chromatic number is 1 and the clique number is 1. If it has some edges, then it's 2 and 2, right? But either way, chromatic number equals clique number. And yeah, this is kind of like, induced subgraphs of bipartite graphs kind of inherit this. They have the same property. They're still bipartite, right? So that's like one example. There are various other examples, so maybe I'll just...
then the chromatic number is like bounded from the...
Yeah, that should be true too. Like if I have a... Yeah, if you have a complete multipartite graph thing like this, then yeah, that should also be a perfect graph, right? The chromatic number is 3, the clique number is 3, and like if I take induced subgraphs, okay, you might throw away, you might just take, but that's also satisfying the property no matter what you do. Yeah, so that would work too.
Are there any other examples? Because this is technically like this is free.
Yeah. Also, if you had, complete four-partite, or like things like disjoint unions of cliques would also satisfy the property. These are maybe not the most exciting examples, but maybe I'll So I'm going to list a few types of graphs that I haven't even told you what they are, but it's not. But just to sort of, in case you come across these in your life at some point, something called chordal graphs are perfect. Chordal graphs are graphs with no induced cycle of length at least 4. So they can have triangles, but no other. So that's what a chordal graph is. People are interested in them for some reason, and they are perfect. Another example is something called comparability graphs. This is like if you have a post set, a partially ordered set, and you make two vertices or two elements adjacent if they're comparable in the partial order. Those types of graphs are perfect. And this actually links to this Dilworth theorem that you kind of looked at on your first assignment. Like the fact that Dilworth's theorem is true is because comparability graphs are perfect. It's actually the same thing. And then there's like other ones as well. So yeah, this is like a kind of abstract definition of a perfect graph. So it might be like interesting to know, is there like a better characterization of perfect graphs? Like, which kind of gives you more information about their actual structure? And it turns out the answer is yes. This is something known as the strong perfect graph theorem. Which says that G is perfect if and only if G does not contain an induced copy. So I mean, when I say induced copy, I mean like it doesn't contain a set of vertices that induces this thing, which I'm going to say, of C2k plus 1, or the complement of C2k plus 1. So this is like this is a cycle with 2k plus 1 vertices for k at least 2. I don't remember if I ever defined complement or not, but in case I didn't, the complement of a graph, well, it's a graph. Yeah, just everything that wasn't adjacent becomes adjacent, and everything that's adjacent isn't adjacent. Like you switch the edges and non-edges. So like what I'm saying here is that you must forbid like a 5 cycle. So because I'm saying it's 2k plus 1 for k at least 2, so like triangles are okay. You cannot have an induced 5 cycle. You could have a non-induced 5 cycle, like that's okay. But you can't have an induced 5 cycle. You can't have an induced 7 cycle, and so on and so forth. And also you can't have an induced complement of a 5 cycle, which turns out to be a 5 cycle.
What do you mean by non-induced 5 cycle?
Like if you had a 5 cycle, like suppose if you see 5 vertices that look exactly like this, that's forbidden. If you saw 5 vertices where that edge actually is there, this is okay. This is not a problem because it's a 5 cycle, but it's not an induced 5 cycle.
Oh, not a subgraph is like literally.
Like literally.
You induce it on some set of vertices. It is.
Yeah. Yeah. So I'm only kind of forbidding induced copies of it. So you could have 5 cycles all over the place, but they'll have to have extra edges in them, like this. Like I mean, or like this. This is also okay, as long as it's not just inducing a 5 cycle. Then you also can't have complements of odd cycles. Okay, this one's just a 5 cycle anyway, but the complement of a 7 cycle is something different. It's like, so you're not allowed to have these, and so on. And if you check these things, like here the what do you call it? The clique number's 2, right? Chromatic number's 3. So you definitely cannot have this in your graph because you're supposed to have chromatic number equals clique number for every induced subgraph. So if this was induced in your graph, it would violate the condition, right? And then you could check that like these things also violate the condition as well. Any questions about the statement of the theorem? Okay, we are not going to prove this theorem because it's like very, very complicated. This was like one of the biggest breakthroughs maybe of like the 1990s in combinatorics. So yeah, it's too complicated, but oh, how do you check what?
The clique number.
It'll be something like roughly the number of vertices over 2, maybe rounded down, because I mean what you should do is take things that are yeah, this one would be 3. I mean, you have to think about how to compute the clique number, but it's not too bad. You take things maybe that differ by 2 until you can't or something. I don't know. So this one would be 2. This one would be 3.
Well, like the only one that will be allowed is the one that like well, for this case, the cycle of length 7 will be
Yeah.
there, but 6 must be there.
So you just can't take consecutive things. And so that's going to give you about half of the, I don't know. I think that's going to end up having chromatic number 4, clique number 3. Anyway, that's maybe an exercise to think about.
Should we have cycle of length 6 though?
Oh, it has cycles of length 6. Yeah, but I'm not. This is not computing the size of a cycle. This is a clique, the biggest clique. So
Yeah, okay.
yeah. So we're going to prove like a weaker version of this. Which is appropriately called the weak perfect graph theorem. Okay. And so yeah, it's not going to give a perfect like structural characterization like this, but this is already very, very valuable because, well, we're going to see, we'll see some examples of that at some point maybe. At least on your assignment you will, but if I have time, we'll see another example. So, right, so the weak perfect graph theorem, it says that G is perfect. It's kind of a strange statement. If and only if the complement of G is perfect. Okay. Which is kind of nice because this allows you sometimes to say, okay, suppose there's some class of graphs you're interested in and you want to know if they're perfect, but maybe it's hard to like prove it. What you could do is just like think of the class of the complements of those graphs, prove that those things are perfect, and then it just implies that these ones are perfect. It's kind of a, and sometimes it's easier to deal with the complements than it is to deal with the original graphs. Okay, so oh yeah, and by the way, this doesn't conflict with this, right? Because the kind of forbidden graphs in perfect graphs, like these cycles and the complements of cycles, they're kind of closed under complementation, right? They're just a family of graphs and the complements. So, you know, if a graph forbids these things, then so does its complement, because it's the same, you know. So what we're actually going to prove is something that implies this. So we'll prove that G is perfect if and only if for every set S, like the size, the cardinality of S is at most the independence number or stability number of the subgraph induced by S times the clique number for all subsets S of the vertices. Okay. And I claim this implies the weak perfect graph theorem. And again, it's because like stable sets and cliques are kind of like the same thing except in the complement or in G. So like if I replace G with its complement, all it does is change this alpha to an omega and that omega to an alpha, and it's like the same thing. So since this is like invariant under taking complements, it will imply this theorem. Okay. Any questions about this? Okay. Okay, so let's first do, I guess, this direction. So we're supposing it's a perfect, G is perfect, and we want to prove this inequality. This is the easy direction. Yeah, so suppose G is perfect. And let's let S be a subset of the vertices of G. And I want to prove that this inequality holds. Okay. Well, so then, because it's a perfect graph, I know that the chromatic number of the subgraph induced by S is equal to the clique number of the subgraph induced by S because G is perfect. Okay. But I can also use one of those trivial bounds. Okay, not the one involving the clique. The one involving the clique number, like it would be kind of pointless to use it right now because I know they're equal. But the other one, right? So the other one says that it's like the chromatic number is at least the number of vertices, which in this graph would be the size of S, divided by the stability number of the graph, which is the stability number of the subgraph induced by S. But like this thing on the left side is the clique. I already proved that's the clique number, right? So, so that's like omega of the subgraph induced by S. So therefore, size of S, if I just multiply over, it's at most, yeah, omega of the subgraph induced by S times alpha of the subgraph induced by S. Okay, so that does one direction. Okay, so I'm just using the definition of perfect and this kind of trivial lower bound on the chromatic number. Okay. Is that good? Any questions? No? Okay, let's do the other direction. Okay, so So I'm going to assume that this inequality holds for every subset. I want to show G is perfect. Let's go by induction on n, which is, let's say n is the number of vertices. Okay. So suppose, to get a contradiction. So yeah, we're also doing it by so it's by induction, and then we're also kind of using contradiction. Oh yeah, and I guess like the case n equals 1 is trivial, so like let's not worry about that. N is 1, chromatic numbers, everything's, anyway, it's going to be true for n equals 1. So suppose that G is not perfect. Now, since I'm using induction, like, I know that every, so for every, well, I guess, so every induced subgraph of G, except for G itself, is perfect. Why? Because, so like, to prove this direction, right, I'm assuming this thing, right, for every subset of the vertices of G. So if I take let's say I take like an induced subgraph of G, well, it's going to satisfy this property because, like, if I take a subset of a subset of the vertices, it's still a subset of the vertices. Like, so if I kind of, let's say I take G and I delete one vertex, that has to be perfect because it's going to satisfy this condition for every subset of the vertices of that graph. And since we're doing it by induction, we know that the thing holds for all smaller graphs. So like, yeah, so it's going to be, every subgraph is going to be perfect. Okay. So the only reason, so in other words, so also then, for every induced subgraph of G, except for G itself, the chromatic number will equal the clique number, right? It's holding for every subgraph. So the only subgraph of G, that induced subgraph that doesn't have chromatic number equals clique number is G, right? So, so for G to not be perfect, we must have that the chromatic number of G itself is bigger than the clique number of G because, it's this thing is not happening for any of the subgraphs because they're all perfect anyway. So it must be that G itself is the only reason why G is not perfect, if that makes sense. Okay. But also, if I apply that inequality where S is equal to the vertices of G, like the whole thing, I get that like N is at most the stability number times omega. So by letting S be equal to the whole vertex set, we get the number of vertices is at most alpha of G, omega of G. Okay. So somehow these things are going to come in handy later. Maybe let's, for a bit of notation, like let's just let alpha be alpha of G and omega be omega of G, just to make it shorter to write things. So here's a claim. So I claim that there exist stable sets S0, S1, up to S alpha times omega in G, such that every vertex of G is an element of exactly alpha of these stable sets. Okay, so I'm not saying that these are distinct, like we could have two of these stable sets being the same or something. I'm just saying there's a sequence of stable sets where if you kind of look at those stable sets and kind of lay them down on top of the graph, every vertex gets covered exactly alpha times. Right? Each vertex is in exactly alpha of those stable sets. Not clear why we would want that, but it's going to come later. So here's the proof. So I'm first going to pick my S0. And it's just going to be an arbitrary stable set of size alpha. So let S naught be any stable set of size alpha, which exists because alpha is the size of the biggest stable set. So there should be one of that size, right? Okay. Now, for each vertex V in S naught, the graph, if I take G, like take away V, so if I delete V from the graph, so this is an induced subgraph because, yeah, it's the subgraph induced by the set of vertices except for V. So this graph can be properly colored with omega of G take away V colors, which, well, by the way, is at most omega. Right, if I delete a vertex, the clique number could only go down. And the reason I know that this can be properly colored with this many colors is because I know all the induced subgraphs of G are perfect except for G. Okay. Is that okay? So then, okay. Imagine I've got my omega colors. Well, as we saw earlier, a proper coloring is the same thing as a partition into stable sets. So each color corresponds to a stable set. And okay, if there's fewer colors, then like let's say I only use omega -1 colors, that's fine too. Just make some of your color classes the empty set, right? And then you've got omega colors. So, so yeah, this gives a partition into omega stable sets. And yeah, like I said, if you've got fewer than omega colors, just call one of the colors the empty set. And the empty set's a stable set. But yeah, so if I do that for every single omega, right? Or sorry, every single V, why did I say omega? Every single vertex V in S naught, there are alpha of those. And for every such vertex, I get omega stable sets. So it's like alpha times omega stable sets in total. So this gives me, so yeah, the stable sets I use in that partition, I just call those, I don't know, for the first vertex of V, call those S1 up to S omega, then S omega plus 1 up to S2 omega, and so on, right? So this gives us, yeah, the stable sets. So S0 was the original one, and S1 up to S alpha omega. Now we just have to observe that everything is covered alpha times. But it is, because any vertex not in S naught, so any U in the vertex set but not in S naught is covered well, alpha times because well, it gets colored every single time, all right? Because we're only deleting a vertex from S naught, so because it is colored in all the colorings, and each, let's say U in S naught, is colored by alpha minus 1 of the colorings, but it's also contained in S naught. So therefore, it's kind of covered alpha minus 1 times from those things, S1 up to S alpha omega, and once by S naught. Okay. Is that okay? I mean, it's not clear why we're constructing these things, but they do exist. Okay. Okay, so we just found a bunch of stable sets. Now let's find a bunch of cliques. So claim 2 is that there exists cliques C0 up to C alpha omega such that SI intersect CI is, well, maybe I think I need to say more. So, well, okay, yeah, I can say this at the end. So anyway, SI intersect CI is empty for, all I. Well, and SI intersect CJ has size 1 for I not equal to J. So this is like for all I and for all I not equal to J. Okay, so, and also the size of CI is omega for all I. So these are actually like maximum size cliques. Okay, yeah.
What about SI?
Those are the same ones, yeah. So I've we found them in that claim, and now I'm locking them in for the rest of the proof. Yeah, yeah. Good question, yeah. Okay. Actually, the key to this thing is just to say, just to prove that, to observe that for any of the SIs, there is a clique of size omega that's disjoint from SI. So first, let's show that there exists a clique of size omega disjoint from SI. And then we're just going to pick CI to be any of those cliques, and then we need to like observe that it has the right properties. So I'm just putting in parentheses that this will be CI. Okay. So I want to do this by contradiction. So I want there to be a clique of size omega disjoint from SI. What if there wasn't? Can anyone see what's going to be the problem there? There's a lot of stuff going on, and it's a little bit, maybe it's a little bit subtle, but so maybe a hint. I want to use the fact that all the induced subgraphs of G are perfect. Yeah, like, well, okay, so let's see what happens. So if not, well, okay. Actually, maybe I do have to think of one case separately. Like, I said that these SI sets, they could be the empty set, in which case when I delete them or something, I won't get a subgraph. But maybe one kind of quick comment, like if SI is the empty set, then it's trivial just because, just take any maximum clique. For CI, okay, so that's fine. If SI is not empty, and if no such clique existed, then the clique number, if I take the graph G induced by the vertices minus SI, would be less than or equal to omega minus 1. Because if there are no cliques of size omega disjoint from SI, then when I delete SI, the clique number goes down. Because, I mean, how could this be equal to omega? It's only if there's a clique in G disjoint from SI of size omega. But then this would mean, remember, all the subgraphs are perfect, all the induced subgraphs. And so then the chromatic number of this graph would be equal to the clique number, right? Which would also be at most omega minus 1. But then I could color my original graph so then the chromatic number of G would be at most omega because I could just color this graph with omega minus 1 colors and give SI a new color. So by giving SI a new color, right? That's not among those colors. But this contradicts something we said earlier. So that would be a contradiction because the chromatic number of the graph we said is bigger than omega. So we kind of derived that earlier. Okay. Okay, I haven't proved everything about this. I haven't proved the rest of these statements, but this is yeah, this proves that I can pick a CI that's disjoint from SI. Okay. So now let's prove that it must satisfy this property. Oh, and also, okay, so we've got this, right? It has size omega. It's disjoint from SI. So all we need is this part. Okay. So recall that every vertex of G is covered by exactly alpha of the sets S0 up to S alpha omega, right? I mean, it says it right there. Okay, so this. So for each I, so what I'm going to do is sum over, so I fixed some I, right? I'm going to sum over all the other values of J and take the cardinality of Sj intersect Ci. So so like Ci has omega elements, right? And like each of those elements in Ci, so if I look at Ci, each vertex here should be covered by exactly alpha of those sets. And it's not covered by Si because they're disjoint. Ci and Si are disjoint. So there must be like, yeah, alpha of the sets Sj that covered that point for every point in Ci. So that actually tells you that since Ci has a size exactly alpha, this is equal to alpha omega. Okay. But, okay, what can I say about Sj intersects Ci as an upper bound? So not from this, but just like no matter what, like if I've got a clique in a stable set, how many things could they possibly share? One, yeah. They couldn't share more than that, right? But then this means, so this is summing over, the number of indices here is alpha times omega, and you're summing a bunch of things that are at most one. They can be one. So the only possibility is that Sj intersects Ci equals 1 for all j not equal to I. Right, because, yeah, the number of indices here is alpha times omega. It's adding up to alpha times omega. Each thing is at most 1. They got to all be 1. There's no other choice. Okay, so I think that proves the claim. Okay. So yeah, this is summing. Maybe I should say this is like summing over, j between 0 and alpha omega, but j is not equal to I, right? So there's alpha omega plus 1 indices, except it's not equal to I, so there's alpha omega indices, so yeah. Okay, we're basically done. So this is kind of the miraculous part of the proof. Actually, I think this whole proof is miraculous. I don't know. Yeah. I'm going to define a couple of matrices. Then we're going to do matrix multiplication, and something weird is going to happen. So let A be the alpha omega plus 1 by n matrix. So let's say the ij entry is, well, yeah, so the matrix is like aij, where, you know, whatever. So I guess the ij entry is equal to, well, sorry, no. Sorry, I need to back up. My bad. Sorry about that. I need to label the vertices first. So let V1 up to Vn be an arbitrary, well, so be a labeling of the vertices. Okay, now A is the matrix with alpha omega plus 1 rows and columns such that aij is equal to 1 if vj is in si plus 1 and 0 otherwise. Okay, I just need to make it, there's something annoying here that, okay, I chose my indices to start at 0. So like, but in a matrix, you start on the first row, not the 0th row. So that's the only reason I need to write a plus 1 here. But, so yeah, this is just looking at, it's asking the question, is the jth vertex in this ordering in Si minus 1? Yeah, thanks. It was one or the other, 50-50 chance, but yeah. Right, because the first row should correspond to S0, and then the second row to S1, et cetera. Okay. Let's do a similar thing, but with the cliques. So B is such that, you know, Bij is 1. Yeah, it's the same thing. So if Vj is in Ci minus 1 and 0 otherwise, okay. And it's also in, you know, it's also an alpha omega plus 1 by n matrix. So I want to think about what is A times B transpose. So the first row of this matrix, let's say, is just like an indicator function of the stable set S0. Like it's, yeah, the first row of this matrix, so there's n columns, right? The first row of this matrix is just 0 for all the things that are not in S0 and 1 for all the things that are in S0. Right? It's an indicator function of S0, or indicator vector. And yeah, all the way down, you get like indicator vectors of all the stable sets in my collection. And then similarly, each row of B is just an indicator function or indicator vector of clique like Z0 up to C alpha omega.
So it would be exactly one in each.
Yeah. Right. So, and actually, more generally, if I take like an indicator vector of two sets and I take their dot product, that's just computing the intersection of the two sets, the size of the intersection, right? Anyone who's in like 414 is like, okay, we do this every day. Yeah. Okay. But yeah, that's the idea. I think you've got the idea that, except here's the thing. If I take S0 and C0, for example, those are disjoint. So those ones will give a 0. Everything else, like, so, you know, I'm going to have zeros on the diagonal and ones everywhere where else. Okay. So this is actually, yeah, what's my number of rows and columns? I think it's, yeah, alpha omega plus 1 by alpha omega plus 1 matrix, right? And if you think about it, this thing has rank. It's got full rank. You're not going to be, because of the zeros on the diagonal, you're not going to be able to make a linear combination that makes 0, right? A non-zero linear combination. So this has rank alpha omega plus 1, the product of these two things. But let me show you that that's wrong. I mean, that's a contradiction. This whole proof is by contradiction, so we want to get a contradiction eventually. Well, so this is a product of two matrices. So the standard thing about like matrix multiplication is like, so if I multiply two matrices, if one of them has small rank, I can't get the rank back by, like, the multiplication is not going to help me. So like, the rank of these things is at most the minimum of the rank of A or the rank of B. Each of these things, the number of columns is n. So like you could not have rank bigger than n, right? Okay, so what we've got is that the rank, I mean, just by looking at it, we can see it's alpha omega plus 1, exactly. But by just thinking about A and B individually, like it's at most n. It can't be bigger than that. So what we get is that alpha omega plus 1 is at most n. But this is a contradiction. I don't know how you like, do you like that for contradiction, two arrows pointing at each other? Or this? Yeah, whatever you prefer. Because we already saw that n is at most alpha omega. This was by taking the inequality in the statement of the theorem. Remember, this was like when we set S equal to the number of vertices, or the set of all vertices. It gave us this inequality, but that's a contradiction. Okay. Do I have any intuition about where this came from? Not really, but it checks out, right? So yeah, it's kind of a magic kind of linear algebraic thing at the end. The original proof was not exactly like this. Maybe it had shared some ideas with this, but people then kept thinking about it and getting it down to like a simpler and simpler proof. So yeah. Any questions about this? Maybe I'll say one thing about like one application of this theorem, which is that you can use it to prove Koenig's theorem. Actually, pretty much everything in this course you can use to prove Koenig's theorem. I mean, we've already proved it directly, and I think like maybe on your third assignment, you've got to prove it using Menger's theorem, and like we're going to prove it again right now, and probably many more times after this. Like everything in this course implies Koenig's theorem pretty much. Right, so Koenig's theorem was that if G is bipartite, then the matching number equals the vertex cover number. And here's another proof. We already said perfect, bipartite graphs are perfect. We already said that. Okay, so by the weak perfect graph theorem, the complement of a bipartite graph is perfect. Okay, so okay, the chromatic number of the complement of G will equal the clique number of the complement of G. So we have to think about what this means for a bipartite graph. Okay, actually, the right-hand side is easier because it doesn't actually, we don't actually care if it's bipartite. So can you see how I can relate this to the graph G? So I want to kind of get rid of the complements and just write something about G, basically. Yeah? Yeah, exactly. So maybe I'll say like, well, so I guess the right-hand side, yeah, is just alpha of G. The left-hand side is maybe a little bit harder to see. How would I color the complement? Suppose you're trying to properly color the complement of a bipartite graph with a small number of colors. I mean, how big could your classes be? Classes means set of things of the same color. So by the way, coloring the complement of G is like decomposing G into cliques, right? Well, the complement of the graph is more complicated than just two cliques because there are some edges going across that were the non-edges of G. But yeah, I think maybe it was somebody saying it. I don't know. Well,
There has to be I don't know if the most or least is n over 2.
yeah, certainly there's some kind of bound in terms of n, because you can't have a, like in G, there's no cliques of size 3 or bigger, right? G is bipartite. So yeah, if I was trying to decompose G into cliques, all of them have to have size 2 or size 1. Right, so imagine I've got some bipartite graph. I could say, okay, that's a clique of size 2. So I'm decomposing the complement into stable sets, which is the same as decomposing the graph G into cliques. That could be a clique of size 2, and that could be a clique of size 1. Right? But the thing is, if I take disjoint cliques of size 2, that's a matching. Right? So this actually turns out to be, okay, what does it turn out to be? I think the number of vertices of G minus the matching number. Because it's like, basically every vertex has to be its own color class, except you can, if you have a big matching, you can reduce the number of color classes by that number, right? Every edge in the matching, you could make that a color class of size 2. Okay, so the left-hand side is this. The right-hand side is alpha of G, but alpha of G is the number of vertices minus the vertex color number. I think we probably wrote that down at some point and justified it. So like, okay, so this is saying, yeah, number of vertices minus the matching number equals number of vertices minus the vertex cover number. So the matching number equals the vertex cover number. Okay, so yeah, I think the only things here to notice, like to think about is like, why is this equal to this? And then like, yeah, the right-hand side ends up being equal to the number of vertices minus the vertex cover number. But both of those things I think are not too bad. But yeah, so then I think this is an easier proof than the one we gave before, right? Except I had to do the whole weak perfect graph theorem to get there. Okay, any questions about that? Okay. But I think this is kind of magic though, right? Because like, actually if you want to prove that the complements of bipartite graphs are perfect, like it's not, okay, it's not impossible, you can do it, but it's not as obvious. But to show that bipartite graphs are perfect is like nothing, right? But somehow then their complements are, then you can get this Koenig's theorem from that. It's kind of interesting. Okay, so, okay, we're, oh, maybe I do want to say one more thing. Remember we had like matching polytopes? So you can also have stable set polytopes for a graph. And also fractional stable sets. So maybe I'll say, so this is related to perfect graphs again. So fractional stable set in a graph G is a vector xv indexed by the vertices of V, or vertices of G, such that so for every clique, the sum of the kind of variables corresponding to vertices in the clique must be at most 1 for all cliques C of G, and all the variables must be non-negative. So it's clear that like if I took the indicator function of a stable set, or the indicator vector, it would have to satisfy this, right? Because you cannot have, like we said, you can't have a clique and a stable set sharing 2 vertices. So this would have to be at most 1, and like it's at least 0. Okay, I think I can write this in 1 minute. We're not proving it, so it's just writing things down. So the stable set polytope is the convex hull of indicator vectors of stable sets. Okay, and a theorem that, yeah, we won't prove, but it is written in the notes, is that if G is perfect, then the stable set polytope is equal to the set of fractional stable sets. The reason I'm writing this is because this is very analogous to what we had for matchings in bipartite graphs, where we said the matching polytope of a bipartite graph is equal to the matching polytope is equal to the set of fractional matchings. And this is like the same thing, but for stable sets. And this holds whenever G is a perfect graph. Okay. Okay, so I think that's all for today.